Yeah, my name is Andrew Szentgyorgi. I'm an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, and I built a lot of instruments over the years. I started out in particle physics, and then I moved into cosmic ray physics. Worked on a proton decay detector. My thesis was on a ground-based gamma ray telescope. Went into X-ray astronomy when I left graduate school. Was an assistant professor at Columbia. Worked on the Chandra optics for a while at CfA, and then since then I've been doing optical ground-based instrumentation, the Hectospec and Hectoshell multi-object spectrograph. Dan Fabricant and I built that. The TRES spectrograph, the instrumentation suite for the Magellan telescopes at F5. And lately, I worked on HARPS North for a long time. Lately, I've mostly been, for the last, unfortunately, I think possibly 14 years, been working on GCLEF, which is supposed to be the first major instrument for the Giant Magellan telescope at first light. I started out in art school, and I hanging around with physicists, I realized that physics was a lot easier than art. A plain piece of paper that you're going to do a calculation on is a lot easier than a blank canvas when you're scratching your head and trying to do something original. There's something aesthetic. I just like making things that are aesthetically pleasing, and building instruments are, there's something nice. And I like optics a lot too. I mean, of the subdisciplines of physics, I've always thought optics was the neatest thing. When you build instruments, nowadays it's got to be a team effort. You need specialties, and you can't know everything. There's a strong tendency to go off and try and learn how to do finite element analysis or something. And what the thing to do is to be able to understand how to talk to the experts and understand what they're telling you and what has value and what doesn't. I hate to say this, but I value good communication skills over genius. Being able to write well is very, very, very important. You will spend a lot of your life writing, trying to explain to other people how to do what it is you need to do. If you want to build instruments, you're always trying to find those technologies that are ripe for plucking. And you're not going to, for instance, learn all about Josephson junctions detectors for X-ray astronomy. When somebody makes one for you, be ready to buy it. And so, I mean, the classic thing right now that with GCLEF is we made a decision that thermomechanical stability for the instrument was the most important thing in the world. And although I would have liked to use silicon carbide, we decided to go with carbon fiber epoxy because it has very low coefficient of thermal expansion, very high conductivity, and it's light. GCLEF is big and weight is an issue. On the other hand, you have to worry a lot about the fact that it shrinks as the water degasses from it in a vacuum. And you have to worry about contamination. Very easy to deposit a monolayer or a couple of layers of sticky contaminants all over your optics, and they will suddenly become opaque to the wavelengths you're interested in. Chandra, HST, and now JWST all have huge composite structures, and NASA has solved those problems. But in ground-based astronomy, you don't have NASA-sized budget. So it's been a real, risk cost management issue for me when I deal with aerospace companies that are used to making a lot more money. If you fall asleep at the switch, you'll find yourself broke and have something that doesn't work. So it's hard. As we go on bigger and bigger apertures, finding ways to make spectrographs for a finite amount of money that have the appropriate resolution to resolve stellar lines is tough. So the challenge is somehow to find a way to beat Liouville's theorem, to find a way to build a spectrograph for, as I said, for finite amount of money out of materials that are in fact available using different tricks. But you have to be very, very careful that those tricks aren't very lossy. You have to keep your throughput up, because if you've jump through a bunch of hoops to build a telescope, build an instrument for a telescope that has a much bigger aperture, but then you reduce your throughput from 10% to 1%, you really haven't won anything, but you spent a lot of money. Well, you know, the overarching lesson that I noticed this fairly early on, and, you know, it's sort of been a guiding principle, and that is that when you're thinking of a new instrument, you really have to involve the observers, and especially the theorists. Theorists, you know, they're kind of out there sometimes, but they really have good things to say. And there are all kinds of great instrumental concepts and cool things and stuff you'd like to do. But if it isn't interesting to the observer community, and if there isn't a theoretical framework that makes it important, if you somehow convince an agency to give you the funding, which does happen a lot, there are an awful lot of done instruments, you'll end up with something that nobody ever uses. And so you have to connect to the science all the time, and be ready to change too. Be ready to pivot. You know, the science that I wanted to do with GCLEF when I first started thinking about it, actually 15 years ago, a very different science now. So you have to stay limber. You have to stay in touch. You have to freshen, you know, your science case. If you designed a really good instrument, you'll find those motivations and context for your instrument. But you got to be alert all the time. You can't just go to sleep and go in the lab and fire up Zmax and not pay attention to what scientists are telling you. In industry, unfortunately, is reducing the number of glasses and many other refractive and transmissive optical components in response to quite legitimate global environmental concerns. My dream material is silicon carbide, and I wish in a perfect universe that silicon carbide was cheap enough to make my mirrors and my optical bench and my optic support structures out of. We were several decades apart if we considered an affordable number. But I think silicon carbide, the miracle material. I also think a concern for me is that the global marketplace for commercial optics, cameras and stuff is moving off CCDs. And I'm really scared that someday there won't be many CCDs to choose from. One of my other mottos is, when you hear the sound of hooves, always think horses, not zebras. But the one truism, as far as I'm concerned, is, assuming you're employed, you're going to spend 8 or more hours a day at work. And if it's not the majority of your waking hours, it's certainly the best waking hours you have. And so you really ought to enjoy it. You know, it should be meaningful. It should, you should be doing things you think are important. And at some level, it should be fun. As far as I know, you only get one life, and you ought to spend it wisely.